Okay, so today we're going to be doing a Norton circuit. So remember with Norton, we short the load, and I'm making this the ZL. This is going to be the load. So you short that. I personally cross it out so I don't use it in my equations. Remember, with Norton, 90% of the time you're going to be using mesh analysis because you want the current through this wire. So I'm going to put the load in the Norton equivalent circuit. So that's 650 at an angle of 90. And your Norton equivalent circuit will always be a current, we don't know if it's up or down yet, ZTH or Z Norton, and then the load, and we get the voltages across the load. Okay? So since we're solving for current, because we want the current through that load, we're going to do mesh I1, I2, and I3. And I've already wrote the equations down, but I'll go over them. So for I1 equation, it's 450 plus 2K plus 5K I1 minus what's between I1 and I2, which is 5K. I1 does not touch I3, so it's 0. If we're entering the negative side here, the positive 15 goes on the other side of the equation. For I2, okay, now we're using this equation, it's negative anything touching I1 and I2, positive for the components touching I2, and then 0 because there's a voltage between 2 and 3 for I3, and we're going in positive, so on the other side of the equation it becomes a negative. Make sure you put this negative when you're putting into your simultaneous equations on the outside of the parentheses for there. Then lastly, we're doing I3. It's not touching I1 or I2, and because the 650 is shorted, the only thing in I3 is that 2K. We're entering in the negative, so on this one, it's a positive 10. Once you put these into simultaneous equations, you'll get your I1, I2, and I3. I don't really care about I1 and I2. I3 is the current that's going through this short. So that is our I Norton. So, and it's positive, so the arrow is going up, and your I Norton is going to be 5 milliamps, okay? Then we have to get Z Norton. We go back to the original circuit, okay? We short batteries, and we put a fake battery where the source is. So let's short that. We short this, and I'll just use a DC battery. So we have a fake battery here, and we minimize the circuit for the fake battery. However, there's a special circumstance here because this voltage here was shorted. If you put a battery or any kind of source, it's just going to go right in this last circle. So you wouldn't have to minimize this because this part of the circuit is shorted out by that short for that battery. So Z total would just be the 2K. Lastly, we have to get our voltage across the load within the Norton equivalent circuit. The easiest way is to put these two in parallel and multiply it by 5 milliamps because that's what's constant in a parallel circuit is that voltage. And I did not figure that one out, so let's just do it now. We got 2K in parallel with 650 at 90. 650 at an angle of 90. Reciprocal angle. We have 618. So Z total for these two is 618.17 at an angle of 71.995. So I would do 8.0, okay? but I'm going to use the whole number and multiply it by 5 milliamps to get my voltage of 3.09 volts at an angle of 71.99. And that is our answer. That's our ultimate goal with Norton equivalent circuit, is to get the voltage across the load within the Norton equivalent circuit. 95% of the time you're going to use mesh analysis to do that. All right, hope you enjoyed it.